Okay, great. Let me start this one. And one more thing that I actually have to say is that there is a shift in two of the categories based on the dependencies. I didn't want to make a discontinuity in the lectures, the concepts that I'm going to present for you. So today I'm going to talk about the statistical signal processing. I was supposed to talk about filter banks and multi-resolution analysis tomorrow, but then afterwards we have machine learning and signal processing. Because machine learning and signal processing is pretty much dependent on what I say today, I actually decided to make a change. So tomorrow, instead of filter banks and multi-resolution analysis, I will talk about machine learning and signal processing. And the next week I will start with the filter banks and multi-resolution analysis and then multi-sensors. I think that's now more relevant to the sequence of the topics that I'm going to bring up. So today is statistical signal processing, tomorrow is machine learning and signal processing, and they are pretty much actually containing the same topics and the same subjects. And there are some more things I've added with respect to the previous semester. Because of the necessity, many students actually tried to do some projects and they were actually delved into some new topics never touched in the course, and also not ever explained in any course like this. I try to actually give a almost complete lecture for some ideas, some concepts, like for example basics of estimation theory. So you don't need to go through the estimation theory in a complete course, because it's really a huge course if you want to go through that, and it will end up a 1 year of studying. I don't want you to go through that, and I don't know actually that 1 year of studying. I just know the amount of which I need in my projects, and that's enough. And also the optimization theory. Optimization by itself includes more than 6 or 7 courses, and nobody can actually say that he can give the course in just 1 semester. It at least needs a period of time, same as your master degree, to just be a professional in the optimization, at least. So that's why I just go through some very rule of thumb methods and algorithms in optimization, those that probably we will encounter in the next lectures, like the gradient descent and so on. You will see later. And also very, very prevalent and frequently used algorithms in clustering. That's why I go to the clustering. I talk about the k-means clustering, and I'll talk about the EM algorithm, expectation maximization algorithm, and density estimations, semi-parametric density estimations, the algorithm which is called GMM, or Gaussian mixture model. So these are really prevalent. So if I can find a slot of time, then I will talk also about the HMM, or hidden Markov models. Otherwise, I will just last it with the GMM, but for the HMM probably I will just upload some lectures or some notes that you can go through that. And let's start today with the statistical signal processing, or as I have named the course as a statistical DSP. Okay. So by now, whatever we talked about in the previous 6 lectures, we were actually meaning implicitly that the signal that we're dealing with is actually a kind of deterministic signal. Deterministic signal means that you can formulate the signal, and if you have an initial point or a point in some distinctive time, then you can definitely draw the entire signal from -infinity to +infinity. That's the type of signal which is called actually deterministic. But rarely happens in practical scenarios that we actually encounter that kind of signal. Mostly the signals that we're dealing with are belonging to a new category of the signals which are called random signals. And as I already explained, random signals like image, like speech, like video, like radar signals, many of the signals that we actually see in the real applications. When we encounter such kind of things, we have to go through a new domain of mathematics. So we have to actually change our mathematics from the basic calculus or just the basic linear algebra to a new type of mathematics which is called statistics, probability and statistics. So whenever randomness comes up, we are somehow dealing with a kind of probability theory. So today I'm going to talk about all the necessary things that we have to know about the randomness. Maybe you'd better to refresh your knowledge about the probability. I will not talk that much about the probabilities. I'll mostly talk about the random processes. The difference between the process and the probability, you will just know it in a few minutes. Then we will talk about some properties and some statistics that belong to every type of the random process, like the autocorrelation function, abbreviated here as ACF, autocorrelation function. Then we have the power spectral density. So the linear prediction as a model, how to model the statistic data, random data, and anything related to that. So as a review of the probability, so what is a random variable? We had a variable in this thing in deterministic signal processing, a variable which is signal, and it can change by time. And here we have a random variable instead of that, deterministic variable. As Sam Savage, has given some kind of definition, it's a number that you don't know yet. You don't know yet. There are different categories belonging to the random variables. They could be discrete or they could be continuous based on what they are going to represent. So it's a kind of mapping the probability of something, the mapping the belief about a kind of random thing, a random entity, to the real axis, to the real values. So, but if, for example, among those real values only 0 and 1 are to be chosen, then it's definitely discrete. But if all the values between 0 and 1 are able to be chosen, so it's a continuous random variable. Then we have some functions related to the random variables, like the cumulative distribution function. We have the density function as a derivative of the CDF. And we have probability mass or probability distribution function. It's a PDF of the signal. It's called the PDF of the signal. It's a function over the random variable. And it's a distribution if it's continuous, and it's mass if it's discrete. Then we have joint distributions of random variables. If we have multiple random variables, then we may encounter joint distribution of the random variables. We have conditional distributions if we have, for example, two random variables. But for example, if we have a data driven from one of those random variables, so one realization of, for example, one of the random variables is already known. If that's given, then what is the probability of the other one based on that? Or in other words, it's like to say that what kind of information knowing about one random variable gives about the other random variable. Then we have the moments or the statistics of random variables, and if we transform a random variable through a system, what happens to the PDF of that random variable? These are the general things that we actually encounter in this lecture. As a review of the probability, the PDFs, we have so many different PDFs based on the applications, based on that random variable is belonging to what kind of process. So we have a normal or a Gaussian random variable. On the top left hand side, you can see the normal or the Gaussian random variable. It's actually normal. It's called normal because normally those variables which are random, they actually somehow represent this kind of function, and that's called normal. In many societies, different societies, you can see that that's really normal to happen. And it has two parameters, or the moments, or statistics. So if I say statistics, or the moments, or the parameters, that's based on the PDF that we have. One is the mean, and the other one is the variance. So let me okay. So for example, for this Gaussian, we have the mean of 0 and we have the variance 1. It's also mentioned here. So here is this red one is actually the variance is 0.2, because the variance is actually a place that you actually reach to half energy of the signal. So, or for a Gaussian, it's actually the place that you get the 95% of the surface below that curve. And we know that for the PDF, because it's a probability, it's representing a kind of probability, so it should sum up to 1. So the surface below the curve of the PDF, or the function of the PDF, should sum up to 1. And how it's represented is actually mentioned here for some specific examples of the PDFs. The normal with these two parameters, the uniform, which actually when we have no idea about a random variable, but we know already that this random variable can get the values in its domain from A to B. The only probability distribution that we can assign to those kind of random variables is a uniform random variable. So uniform random variable is a kind of Gaussian with the variance of infinity. We have no idea, but because it has to sum up to 1, then we have here the function value to be 1 over b minus a. And we have, for example, a gamma random variable, which it could be used, for example, for some kind of sparse random variables. We will come back to this later. And here, for example, we have a shape and scale parameters. So these are the different random variables from different classes, and they have their own application based on the application that you actually you're going to do. So for the noise, normally we use the normal noise or the Gaussian noise.
For the first picture, what is it for the y-axis?
The y-axis is the value of the PDF.
Okay. Not the variance, right? The variance is different.
here we have the value of the PDF over
This is a mean.
over the x, which is the random variable value. So when you realize the random variable, it gets its values in this domain. If it gets the value below this curve, it means that most of the values of x are 0. So it has the most, if you count the number of times that x random variable gives you 0. Then if you count it, you put it here. So it's around 0.9. Then you count how many times you get 0.2, for example, for the x. You count it and you come up with, for example, 0.75. Then you count it how many times it will actually result or realize as 1. Then you get something like 0.05. Then for a case of, for example, how many times you can come up with x to be equal to 2, you see that almost never. So that's how you can explain, get the information from this kind of curve. Yes?
How does this gamma distribution differ from normal, the Gaussian? Because
This one.
I think, yeah.
This one, you see here, you have a symmetry around the mean. Here you don't have the symmetry around the mean. So mean is here. For example, in this one, you have, here you don't have mean actually. What you have is the shape and scale, that's all. So the shape and the scale. For example, here you don't have any symmetry. You don't have any symmetry. Even though in some cases you might have symmetry, but not necessarily for all the cases you have a symmetry, around the median. Or
So here the k and theta are the two parameters for the gamma distribution.
KLD.
No, for the gamma distribution, what are the parameters? The k and theta are the parameters.
The parameters are shape and scale,
Okay.
nothing else.
Okay.
We don't talk about the variance. We never talk about the variance. We just say that shape and scale, that's all. Okay, there are some important theories and sometimes axioms regarding the random variables and the random processes. I'm going to very fast talk about these theories, and then we skip through the random, the probability, and we go directly to the random signals. One of the important theories is central limit theorem. What it generally says is that if you have different random variables, so if you have, for example, n number of random variables, and they are all having, taken from similar PDF or distribution function, that distribution function actually has a variance which is limited, so not having uniform distribution, just having a limited variance. Then superposition of these random variables will actually get closer and closer to the normal or Gaussian distribution. So it doesn't matter what's actually the PDF of that random variable, whatever it is, the Rice, the Riley, gamma, whatever. Just if you add up several random variables, I'm not talking about how many, because it's another parameter. We have to actually figure out how many based on different PDFs and their variances. But if you add up the random variables, you're actually, if they have a limited variance and they are all taken from the similar PDFs, then when you add up these random variables, finally the result will actually try to, it has the tendency to go through the Gaussian random variable. Finally, it's actually have the tendency to the Gaussian random variable. That's the entire idea of the central limit theorem. And it actually plays a very important role when we talk about the ICA algorithm. So the ICA is a method for separation of the sources based on the prior information that they are independent. And one of the most prevalent algorithm in the ICA is based on theory, which is actually taken from this CLT or central limit theory. So we have the mean and variance for many of the PDFs, like the Gaussian. The mean is the first statistics, is mean or expectation. So the definition of this moment is like this, m of x or expectation of x, which actually depends on the PDF. So it's an integral of x times the PDF of x. So the probability which should be assigned to that x. So we can, it's like averaging, but while averaging, you're actually giving weights to every x. So every x takes its own weight. That weight is actually taken from this PDF, and you average over the entire domain, which x can actually get those values. For the case of variance, you're actually trying to figure out how the values of this random variable is actually spread around the mean. So if x is the value realized from that random variable capital X, then if you center this value around the mean and give that weight, then this is the equation which actually represents how it's the energy of those the realization of the random variable around its mean is called the variance. In many cases, we don't have access to the PDFs. If we have the entire data, then probably we can assign a kind of PDF to that. But what if we don't have access to the data, the complete data, or we have just partially seen the data? If the data is partially seen or observed, then we're not able to actually take these statistics like the mean or variance, because you saw that the weight is P of X, and that's the PDF of X. We don't have access to the X completely, so we're not able to know what exactly should be that P of X. But there are theories try to approximate those P of X, or at least those statistics, and using, for example, the samples or the ensemble method or the empirical mean or empirical the variances. These are called the ensemble methods. And for example, for the case of mean, it has been proven by law of large numbers that we can replace the mean, as we mentioned in the previous slide, the first one. We can replace that with this equation, which is actually taking the average over a window of realizations of that random variables in that window. So whatever, for example, we have the stream of data. It's called xi, or the sequence which is called xi. I varies from whatever to whatever. But we take a window of that which is available, and you can just assign the indexes from xi, from 1 to n. That's the size of the window. And then if you take the average can be also called as mean, and this is a very good approximation of the mean that we mentioned in the previous slide, which theoretically is actually the mean that should be based on the probabilistic theories. So here we are actually getting the sample mean. That's a sample mean, and maybe in the future you will actually encounter such kind of definition in Monte Carlo methods. Monte Carlo methods, actually, they are using the sample theory. They are doing the sampling instead of taking the real P of X, because we don't have access to that, so they use the sampling theorem in order to get the statistics of the data. So the sample mean is just taking the average over a number of parameters, number of the realizations of that random variable. And the sample variance is, by definition, just the variance or scattering of the data energy around the mean. So that's the scattering of the data energy around the mean. So you put the data, you actually subtract the mean of the data from the data, and then the energy of that, when you average it over the entire window, gives you the sample variance. So there are other definitions which actually come up when we talk about the process. So let's first go to the process, and I'll come back to this definition of the autocovariance function as a sample autocovariance function. So now let's talk about the random process. It's a kind of generalization of random variable. When we talk about the random variable, we never mention anything about the time. We assume that whenever you take a realization of the random variable, so you have a random variable. So that's a random variable set, or the variable which is producing everything in random based on some kind of PDF. Then you realize, for example, 1,000 data out of that. You never mention about the time. But the random process generalizes this idea. For example, it says that take 1,000 samples out of this PDF, but over the time. And if you do that, for example, infinite amount of time, then it would be a continuous random process. And if you do that, for example, in discrete time samples, then it's a discrete random process. So it's a three-dimensional entity, actually. I can just simplify that by this kind of drawing here. Assume that we have a random generator. So this one is a random generator. And this random generator outputs the data based on some PDF. For example, a Gaussian or a random normal PDF with some mean and some variance. Then realization of that, for example, for 12 hours, will give you such kind of, for example, stream of data, something like that, for a 12 hours period, starting from 8 a.m. to 8 p.m. If you do that for several times, n times, in n different days, each day you will get something. So now the point is that adding the entity of time to the realization is actually making it as a process. Now the point is that if you take, for example, a distinctive time like t0, and you take the samples for all these realizations, from 1 to n. Here you have, for example, this one. Here you have this value. Here you might have this value, and so on. So if you take these values, this is one realization of that random variable, x at time t. So this realization is actually here is xt0, the vector of xt0. And if you do that, for example, at time t1, you get xt1, a vector which actually this vector represents the values of the realizations over the time t1. Okay? So this set is actually now representing the random process, x of t. Is now the random process, which actually is a random variable over the time. So you have a three-dimensional space, actually. I could draw everything in the 3 dimensions. And in the books, normally it's in 3 dimensions. One is the time, the other one is the PDF, and the other one is the value that you get. So Now, whatever theory that it can, or the terminologies that come out of that random process. One is the stationarity. The stationarity of the random process, when we say the random process is stationary, it means that statistical properties will not change over the time. Simply, using the figure I show here, it means that, for example, if you realize the random variable over this, for example, n days, if you take the random variables, the random variable at this time as xt0, and you extract out the mean and the, for example, the covariances, the mean is a vector, is a value, and the covariance is a matrix, for example, or we can say the variances, just simply the variance at time t0. And it only, because of having the Gaussian distribution, it only has these two statistics, mean and variance. No other statistics. So there is no higher order statistic, the first order and the second order, because it's Gaussian. If it was not Gaussian, it could have so many other things, so many other statistics. So stationarity means that if we take the parameters of this random variable, realized from the random process at time t0, and then we extract out the parameters of this random variable realized from this random process at time t1, if that process is stationary, then this value equals to this one, and this value equals to this one. So the means and the variances are the same. Yes?
Could you please give an example for a stationary random process?
We have stationary, and we have white sense and stationary, and we have the strict sense and stationary processes. When we normally talk about the stationary, we're talking about the WSS, or white sense, or relaxed version of stationarity. So for the noise in the environment, even though it's changing over the time, but normally it's a stationary random process. So ambient noise, or the environment noise in the room, is actually a white sense and stationary process, WSS. Electrical noises in the devices is normally the WSS, white sense and stationary. The speech signal over the short time periods, short frames, is when the frame is less than 20 milliseconds, is almost stationary. When you get longer frames, like 100 milliseconds, then it's not stationary anymore. Okay? So if the statistics is not changing over the time, then that process is called stationary.
So the statistics include only mean and variance?
If the PDF is,
It's a Gaussian.
Okay.
I already talked about the PDF. If the PDF is Gaussian, then it means this.
Mm-hmm.
If the PDF is Laplacian, then these are just the first and second. But you also have higher order statistics, the third order, fourth order, up to infinity.
Yeah.
Now, we have the WSS stationarity and strict sense stationarity. So WSS, which normally happens in the processes, the real application processes, means that only the first and second statistic, the first and second order statistic, remains the same. So mean and variance. But about the higher orders, we have no idea. Then that process is called WSS. But for the strict sense stationary, it means that all the statistics, by changing over the time, should be remain the same. And it's very hard to actually verify that, whether all the higher order statistics also remain the same or not. It's very hard to verify that. That's why most of the cases we are actually having this relaxed form of the assumption, which is WSS assumption. So that's the meaning of stationarity, and that's the meaning of, this is the meaning of White-Stetson stationary, which means that only the first and second order statistics, which are mean and variances, are the same when you are evolving over the time. You got it? Okay. If you do this averaging, this kind of averaging, it's called ensemble average. This mean is called ensemble average. And if you take the average of one realization over the time, here is also you have a random variable, and it's also taken from that process. Now, if you take the average over the time from this one, that's called timed average. So, averaging over the time is called timed average. Averaging over the realizations of one random process over, across one time period or by evolving the time. So this vertical actually averaging is called ensemble average. Time average, ensemble average. Now the point is that we call the random process to be ergodic if the timed statistics is equal to the ensemble statistic. So we call a process to be mean ergodic if ensemble mean equals to the time mean. And we say that's the process which is variance ergodic if the time variance equals to the ensemble variance. You got the idea? These are the definitions. So, passing through those initial definitions, now let's talk about some really useful functions of the random variables. Yes, please.
I didn't clearly understand what is this 1 to n. The first signal is clear, so we take at the time instant 8 or something like that.
Assume that this is the 1st of January. You run this random generator, and from 8 a.m. to 8 p.m. you get this data, which is random.
Okay.
Then you go through every day until the end of the December.
Okay.
For 8 hours you gather the data. That's the data gathered for one complete year, or 10 years. Then at time 10
Yeah, okay.
of any of these realizations, if you get the data, it's called the ensemble data. An ensemble mean corresponding to that ensemble variance. But if you get the data here from 8 to 8 for one day, and then take the mean and variance or whatever, it's called timed average, timed variance, time.
So this
Higher
would be useful for predicting, like, people want to do, what will they do in the first thing in the morning over the course of time?
We have so many processes that it's important to get the information over the course of time.
Yeah, okay.
Like the stock exchanges, like the oil prices, like the crisis in the world, like the terrorist activities, like whatever that includes a kind of time. So you need to get some information to gather the information out of this kind of process, which evolves over the time. If you get some data over the time for 1 year, for one day, and then generalize it to over 10 years, 20 years, then you will get the PDF of that data. What kind of process it actually represents. Then you can generalize that idea, that information, that functionality to whatever is going to happen in the future. You apply that for the future. So sometimes the future is not coming, but you can you say that, okay, I know that this is a stationary process. It doesn't matter whether I go to the time or to the ensemble. I have some ensembles or empirical data from last 10 years. I can generalize that to the future. When time is the matter that you cannot deal with, try the empirical data that you already have. If time is not the matter, the empirical, you have lack of information over the, you have lack of the realizations, then take the time. So you're playing with two quantities based on your application, this one or that one. If you know the process already is ergodic, you can do that.
Okay, you said in process ergodic, you said at a particular time slot, like 10 p.m. let's say you have.
For example.
Yeah, and then you collect that data, statistics data, and you say that it's similar to like the December 1st data. That's what you mean, right? Like the ensemble characteristics have to be same as the.
Given that the process is ergodic,
Okay.
given that the process is ergodic, ergodicity is a property of that process. Given that the process is ergodic, then you can have the time average or variance, or you can have the ensemble average or variance. They should give you the same if it's ergodic.
Okay, not the reverse.
Not always.
Okay.
You got it? So, other things related to random processes, for example, the autocorrelation, autocovariance functions, these are really, rule of thumb, and they are things that come in handy in many cases. So, autocorrelation function, autocovariance, and power spectral density, which is actually the Fourier transform of autocorrelation. So, if you want to actually move from the time domain to the frequency domain to the Fourier domain and get all the informations that we already had in the autocorrelation function in time, you want to get it in the frequency domain, then you just map the function into the frequency Fourier domain, and what you get is called PSD, or power spectral density. So autocorrelation actually measures how the random process changes over the time. If there is no change of the random variable, so the autocorrelation function is actually 0. So it's very useful. We see that in the array processing, for example, to get the information of the DOA, or direction of arrival. We'll see that when we want to know that, for example, what is actually the time difference of arrival for a signal, for a source signal, acoustic signal, to be captured by one microphone with respect to another, which we already know the geometry of those microphones, or the distance between these two microphones, we can easily apply the autocorrelation function. Because we know that a signal which is acoustic actually is propagated over the time, and we know that the speed of propagation is something like 340 meter per second. So we already know that the difference between these two microphones is, for example, 20 centimeters. Then it's clear, if we take the autocorrelation function between the samples that we have in one microphone with respect to the samples that we got and captured in the other microphone, and then try to make lags, so changing the phase of the signal or give the delay to the samples, whenever they match, they will give a peak. And that delay, the number of samples that we made, actually the lag for any of those microphones, and this peak actually obtained, those number of the samples based on the frequency of sampling represent easily what is the time difference of arrival. So it actually tries to actually returns us back to the position of that source with respect to each of these microphones. We will come up to that idea in the GCC function in array processing for localization of the sources. Autocorrelation function can be used in many places. Extracting the pitch of a signal in the speech. If you want to extract the pitch, which is one of the frequencies, the fundamental frequency of every human body, is called pitch, and to extract it we can use the autocorrelation function in many places. autocorrelation somehow represents the similarity. So autocorrelation is actually showing the similarity between two random variables. If you want to know how much two random variables are similar, you use the autocorrelation function over those two random variables. And its equivalent in the linear algebra is dot matrix, dot product. So it's very useful. There is a theory which is called Wiener-Khinchin theorem, and it says that power spectral density and autocorrelation are the Fourier pair. So if you have the autocorrelation function, then take the Fourier of that function. Easily you go to the frequency domain and you get the PST, or spectral density of that random process. Let's talk about the moments of the random process. So we have the mean of the random process. This mean, if it's constant, it means that that process is WSS. So in general case, I have represented mu as the mu of t over the time, but it doesn't necessarily changes over the course of the time, because it might happen that the process is WSS, white stationary, and then it means that expectation over that process is independent of the time and it's always constant, and is mu. The same thing for the variance, which is the second moment. And for the covariance, if we have two random processes, xt and xs, you want to get the covariance, is simply expectation of any of those realizations of the process at time t when it's centered around its mean. So you get the mean out of that random variable for any of those random processes over the time t in the realization of that random process, and you simply take the expectation of this one dot the other one. So it's like the dot product or the similarity case. Whatever expectation you get is actually the covariance function. Correlation is actually the covariance which is normalized over the standard deviation or over the variances. So the correlation function is the covariance which is normalized by their variances. The same as, yes?
By the standard deviations.
Standard deviations, yeah. The same as what we talked about, the sample variance and sample mean, we have sample covariance. And sample covariance is just like to say, you take, for example, you have realizations of a process, stationary process like this, x of t, capital Xt. You get a realization, and if you want to calculate the autocovariance, it means that for that random process, you're actually taking the resemblance or the similarity of that random process with some lagged or delayed version of the same process. If you say the cross covariance, it means that you have two different processes and you're actually taking the realization of those processes and then taking the similarity between the realizations of one process with the other one. So in general, if you have one random process, x over the time, and assuming that it's WSS, then the realization of this process would be x. For example, n number of the samples, we got it from this process. And we put it, for example, in the time sequence of x1 and xn. Then when we say Rxx, so the same process, similarity with the same thing, it's actually autocovariance or autocorrelation. So that's the expectation of X transpose in a vector form. But when you have X and Y, which are taken from two different random processes, then you have cross correlation and you have the expectation of X, Y transpose. And for the autocovariance, it's just centered version of that. So for the autocovariance, we write it down as X bar and X transpose bar. And for here, X bar, Y transpose bar. So it means that you have taken out the mu of X from the data. And here you have taken out the mu of Y and mu of X from the data. Then you have the covariance function. And for the sample version of that, you have just the number of the samples, n number of the samples. You take the average over the samples instead of expectation. You just replace the expectation function with this one, with 1 over n sigma. That's all. So whatever you are supposed to put here, you can put it here. Okay. When we talk about this strict sense and stationary, we already said that we need to have all the higher order statistics to be the same over the time, and they should be the same. But the problem is that getting the information of the higher order statistics is not easy. So that's why it's very hard and difficult to verify the higher order statistics. And we skip through the SSS or strict sense stationary processes in most cases. In general, getting the PDF is not simple. So we don't have access to the PDF, and we prefer to have a sample version of that. When we say IID, samples are IID, is an abbreviation for identical, independent, and identical distributed. So it means that when the samples are IID, it means that every sample is independent from the other one, and at the same time they are taken from the same PDF. So for example, they are taken from the Gaussian PDF with mean 0 and the variance 1, but every sample is independent from the other one. Okay? And when samples are independent, then we are sure that they are also uncorrelated. So independence is the highest degree of or the strict case of two random variables to have nothing to do with each other. But correlation is just to the second degree. So if we have the uncorrelation and we have other higher order statistics also not related, then it becomes independence. So verifying the independence of two random variables would be very difficult, because we have access mostly to the first and second statistics, but not the higher ones. So, yeah, whatever I mentioned here for the case of autocorrelation, autocovariance, also mentioned here. Autocorrelation normally is written in the form of R. If it's autocorrelation, so we have X and X, two random variables which are taken from the same process, so we call it X and X, because they are the same. But they just belong to different times. One is belonging to the time n, the other one belongs to the time m, And in general, we just put the conjugate here, or transpose, doesn't matter. If you have a vector, then it's better to make it, transpose. And if they are continuous, you put integral. If they are discrete, you just replace it with sigma, summation or sigma. And for the autocovariance, you take out the means from each of them. And if you can tell me if these two random variables xn and xm, if they are white sense stationary, it means that by changing over the time, nothing changes. So the correlation function only depends on their time difference or the lag. So for the white sense stationary, for WSS processes, it's written that Rxx of xn xm transpose equals to Rxx of is a function of, in general, is a function of, forget about this, is a function of n, m minus n. So just the difference in time, or the lag, which is called the lag, that's the only thing that they depend on. And that's how we use actually the GCC function for localization of the sources. We will see later. Okay, so far we talked about different properties and theories. Very briefly, what different theories we have around the random processes and random variables. Now it comes the time to explain how we can model the random process or random signal. Signal is actually a sequence of data which are randomly taken or which are taken from a random process. So when we talk about the speech signal, it means that every sample of that signal, the vector of the data samples that you're actually getting as a stream of data, is a realization from a random process. For example, if we assume that the speech signal is taken is a kind of Laplacian PDF, is having a Laplacian PDF or generalized Gaussian PDF with some variance, with some mean, then it means that every sample of the sequence of data that we get as the speech signal is one realization of that, or one sample taken out of that PDF. Now the point is that how we can generally model the data, any kind of random data. If we have a stationary processes, then there are some methods, some mathematical forms already driven just for the case of the white sense stationary or general stationary signals, random signals. One of them actually goes back to the WOLD theory, WOLD decomposition theory. There are two different things. One is WOLD decomposition and one is WOLD theory. They are different. So today we're talking about, here in the course, we're talking about the WOLD decomposition theory. What it generally says is that any stationary process, any white sense stationary process, like x of t, it can be expressed as a superposition of two components. Two components. One is a stochastic component, like the white noise actually given to the filter. And the other one is a deterministic component, which is actually irrelevant to the first part, or independent from the first part, or uncorrelated. So you can just see it in the Wikipedia. It's a very good definition of the WOLD decomposition theory. But it actually plays a very important role when we talk about the linear prediction or the AR modeling. So, what it actually says that if you have a signal which is stationary, WSS, you can simply write it down as a linear combination of white noise processes. It means that you can have a white Gaussian noise in the input of a filter which is moving average, and that gives you the signal which is WSS. So if the process that you're dealing with is stationary, we can immediately understand how we can model that kind of signal. And for example, for the case of speech, if we have window which is smaller than 20 milliseconds, we know that the speech signal represents a stationarity, or is WSS. So as soon as we know that it's WSS, we can easily model that speech in the short time windows as the WOLD decomposition says. Yes?
Is a white noise process with only white noise, or is it a signal with additional white noise?
No, it's actually, it's just the same as we are actually feeding white noise to a system. This is really a white noise. So you can call it N, which N is actually taken from a Gaussian with mean 0 and variance of sigma square. That's really a white noise, Gaussian or normal. Normally you see such a thing. You feed the white noise to a filter and you get the signal which is stationary. That's how it's represented. So here you have a system and you have to get the parameters of the system. So those parameters of the system can be learned from the data. And that's what we actually do in the linear prediction. Linear prediction actually does it. And this is actually how the source filter model of the speech comes up. Source filter model, I'll show you later, that is exactly using this WOLD decomposition theory. ARMA models, or autoregressive moving average models, are very good approximations to the WOLD representation. And we will see in the first couple of slides that how it actually applies to the modeling of the white sense stationary signals. So it's like that. We have a white noise, nu of n, or whatever name you want to put for it, that it has the variance of sigma square, or in the PSD form, we just have sigma square because it is white Gaussian noise is white. So the energy of this noise is always for all the frequencies the same. That's the white.
Here we have the variance as the parameter to control the amount of white noise, right? Or is it like that? Or?
Variance of the noise is something that controls the SNR, signal to noise ratio.
Okay.
And then the less the sigma square, it means that the quality of the signal you can get in the output is much better.
Okay. So the
When we say,
is to control
yeah, that's how we mention, actually this is how we use the power spectral density, and it means that how much energy for that signal is over the frequencies, different frequencies. But for the white Gaussian noise, when we say white, it means that the energy is uniform for all the frequencies and it's constant. And what is that constant? Is sigma square, which is the energy of the noise, the variance of the noise. That's the meaning of white Gaussian noise, WGN. And you're actually giving this white Gaussian noise, based on the WOLD theorem, decomposition theorem, you're actually giving this white Gaussian noise to a linear filter, LSI, LTI filter, and you're getting a signal, random signal, which is WSS. That's the result of the WOLD decomposition theory. And when the signal passes through, when the signal, which is here is noise. Noise is also a signal. Don't forget, when we talk about the signal in general, it doesn't mean it also, it should for sure give us some information. No, noise is also a kind of signal. It's also a signal, and it has more information than any other signal. Because for any other signal, you have a kind of belief or some prior information about that, but for noise, you have no idea. So every sample of the noise is really informative, but every sample of the signal is not necessarily informative. So noise is also a signal. So if you pass or feed the noise to a filter, which is LTI, and what you get is another signal, then based on the LTI models, the power spectral density in the output is actually the square magnitude of this LTI signal system or model times the power spectral density of the input. So that's the power spectral density that you actually observe in the output for that signal, x of n, which is WSS. Now, there are different models that you can put here. They are called, in general, they call it ARMA models, but they can be AR, or can be MA, or can be ARMA. AR models are autoregressive models, which are all pole systems. So they all, they just have poles. There is no zero. MA, or moving average, the other way around. It just has zeros and not even a single pole. And ARMA is a combination of these two. Okay? But it's clear that if you use AR or MA, you have less parameters. If you have ARMA, then you have more parameters. For the case of AR model, which in the spectral theorem is actually proven that AR model is a very good model to model actually many of the random signals, which are WSS. One of the best and simplest models that you can assign for is AR model. It's how it's represented. So we have the signal x of n in the output. You have the nu of n, which is the white Gaussian noise, in the input, and the relation, how it comes, is actually like this. So the filter is like this, 1 over 1 plus this. You can also represent this using the Z transform. It's simpler to have it with the Z transform. And if you just replace it with the Z transform, it's just 1 plus akz minus k. Okay? For k equal to 1 to n. So we have n number of parameters in the AR model. And these are the ak values. These are the parameters that you have. AK values. So you can train these AK values for a data, and then during the test time, you can just use those values. It has been proved that, for example, for the speech signal, when you have short time windows, less than 20, 30 milliseconds, which almost is WSS, then K or N equal to 13 or 14 is enough, or even 10 is enough to have a very good approximation of that signal in that period of time. So it's not too much parameters. It's just 10 up to 14 parameters, and you can train that easily with the data. But you see that how simple you can use this for the compression as an example. And it has been used for decades for the compression of the speech signal. The algorithm is called LPC, or in the very early versions of the mobile systems, which was called GSM. You have probably heard about that. They were using actually KELP coders or RPE LTP coders. I'm actually going back to this. Just let me show that. So audio codings we had the initial version, which was PCM, using the mu law, which you have, for example, 8 kilohertz of sampling, and definitely if you have 8 bits for each sample, then you have 64 kilobits for each actually sample of data for each period, for each frame. But if you go through the GSM, which uses this LPC or linear prediction, it actually downs to 13 kilobits per second, and for the military applications it uses LPC, which actually downs to 2.4 kilobits. So you see how much compression you can get. Why such kind of compression? It's very easy. You actually come up with that compression because you're assuming that the signal in 20 milliseconds is white sense and stationary, so you don't need to pass this 20 milliseconds of signal. 20 milliseconds is almost 512 samples. And if you take the samples with, for example, 16 kilohertz, so you have 512 samples with 16 kilohertz frequency of sampling. And you have to assign 8 bits for each of these samples. So that's the amount of memory you use for one frame. But the point is that in this 512 sample window, because the signal is white sense and stationary, you don't need actually to pass this 512. The entire thing that you need to pass is just AK values. And that's just 10. 10 real values, that's enough. Because the signal in that window can be represented based on AK values, which varies from K1 to K10, for example. So the only thing that you need is just 10 values from AK and the variance of the noise. So you have these 11 values, put it in 1 byte for each, and that's all you need for every frame. And then in the output, in the receiver, you do the reverse process. Synthesize the signal based on the LPC coding. So that's why it was called LPC coders. They are coding. They are used for the compression. That's just because of the WSS processes can be represented as it's mentioned in the WOLD decomposition theory. So, we see that a R model is a very good model to represent a WSS signal, whatever signal it is. We don't just we never resort to a speech signal. And if you just rearrange this and rewrite that, that's the error of the signal. And if you want to get the values of AK, you have to solve an optimization problem. For example, using the minimum square of the error as a measure of the optimization. But this measure of optimization means that this error, which is actually the difference between the true signal and the filtered version of that error should be minimized in the square sense, which is a quadratic problem, a quadratic optimization problem based on these AK values. That's what we have to solve. And we will actually come to this in tomorrow, actually, when we talk about the optimization problems, how we can solve this kind of problems. So simply using this, we can come up with the Yule-Walker equations. So I'm actually, let me show you something. Maybe it's better to jump to one of the notes that I've already put in the website. So this is one of the things I put in the website. Is the linear prediction derivations. That's the problem. It just shows the PowerPoint, but it should also show the okay, I think it's clear now. So, in order to derive the variables of the linear prediction model and how they are derived, actually it's in a very short 3 pages of document that I've written by hand. So how can we approximate the current value of WSS, or a stationary random signal process, based on these past values? It's in linear prediction, but maybe first let me talk about this linear prediction in more detail then. So the WOLD decomposition I already talked. Every WSS process can be represented based on the WOLD decomposition theory. But the point is that the idea of linear prediction uses this and says that for signal, which is WSS, I can predict the next sample based on the previous samples. So I can have x of n represented based on the previous samples. So k equal to 1 to, for example, n minus 1. ak x n minus k. So we can use previous samples of x if the process is WSS. For every sample at time instant n, you can use just the previous or the past samples. Here n minus 1 samples, but there is an error. So that error we can represent it by nu of n. Error of this approximation would be nu of n. Then if you write it down, if you just take this sigma to the other side, to the left hand side, so it's quite similar to what we had in the AR modeling. The only thing is that for these coefficients, we have the negative value of those coefficients. So ak is replaced by minus ak. But it doesn't matter. You can just use the alpha k as minus ak. And then you come up with the same thing. Exactly the same thing. Okay? So here you've got minus ak x n minus k for n minus 1 value. And here you have the noise. So that's quite similar to what we had in the AR modeling. So linear prediction says that I can use the WOLD decomposition theory for any WSS signal to model that signal at any time instance based on its previous samples. Based on the previous samples. But how many samples? It's enough, experiments show that it's enough to have, for example, 10 samples, 14 samples. You can have more samples, it depends on your application. but it's enough to have quite a few number of the samples from the past, and then you can represent the signal in the time domain in the instant time based on its previous samples, and the white Gaussian noise as an error. So this white Gaussian noise is actually the error of this approximation, that it has mean 0 and the variance. It's quite similar to say that there is a white Gaussian noise fed through a system which is AR, and you're getting that WSS signal. The other way of representing the same problem. And linear prediction uses this idea for the speech case, for example, a speech production model. And you see that that's quite the same thing. That's called the source filter model for the speech. So how it's modeling everything that actually is the outcome of the speech, it says that whatever phonemes that comes out of the mouth of the talker, the speaker, is either vowels or the consonants, or voiced and unvoiced. Maybe it's better to say that it's voiced or unvoiced. Those phonemes which are voiced, they are actually as a result of fluctuations or vibrations of the vocal cords. And that vibration is creating a kind of harmonical with the impulses. So that's like a train of impulses. And the other part, which belongs to the unvoiced, is normally similar to or very approximated with the noise, the kind of noise. So that's called pseudo noise. So the input would be either the impulse train coming out of the vocal cord with some fluctuation, with some vibrations, and that frequency of the vibration is the pitch frequency. Or actually it's coming from the mouth without triggering the vocal cord and is a pseudo noise. So one of these two should be the input at every frame, and then it passes through the AR model.
Could you say the formula again?
Yeah. Sorry, I forgot about that. So the input would be impulse train as a result of the vocal cord vibrations or something like noise, pseudo noise. And this input is actually fed to a system which is AR, modeled as an AR process. And this AR process, these are the values, these coefficients, are nothing but the parameters of the vocal tract. So there's a pipe from the vocal cord to the mouth, and this pipe actually something that is a mechanical tools. It actually takes the energy, the signal, the pressure of the signal, and it also has some natural frequency of resonances. And this AK depends on those parameters, those resonance frequencies. And then finally you have the speech and the output of the mouth. In a more general modeling, we have a high-pass filter also here, which somehow shows the radiation of the lips as the high-pass filter. But we can actually forget about that in general. That's why we say that every speech signal at time n depends on its past time, the p-values in the past samples in time, plus something that comes from the input. And this input would be either the impulse train or a noise, complete noise. So that's how we model. And it's called the source filter model. Source filter model for the speech generation. So the derivations of that is based on the linear prediction coding. So we have x of n, sample at time n, or the instant time that we are, the current time, is based on the previous samples. How many samples? P samples, for example, in general P, and in P can be trained. And there is a noise or the error of this approximation, and this error could be with zero mean and the Gaussian PDF. So that's the approximation of the signal. What we have to do is, in order to get those parameters, those AK values, we have to minimize the mean of the square of that error. So the mean or the average can be taken in the sample form. So we just replace it with the sum instead of using the PDF, the average form of that. And then for the training data, if you have the training data, so it means that you have the current and the past samples for every training data, you can just use it for every frame. You get the AK values that minimizes the energy of this error. And when you have this for the training data, you can simply use it for the test data, the AK value for the test data. That's the LPC analysis. And how the derivations of this LPC is, as I told you here, here it's mentioned. So the derivation actually comes to this point that we have this cost function, which is the energy of the noise, which should be minimized. In order to minimize that and get the parameters, we need to take the gradient of that based on the parameters. So the first derivation based on the parameters, which are AK, the model parameters are AK, and then make it equal to 0, getting the stationary points, and we have actually the AK values. We use this idea that noise is independent from the signal. So we have the eq'n, we have the x of n. We can replace them. It's actually using the autocorrelation function. And the noise is actually, the error or the noise is assumed to be Gaussian and white, similar to what we had in the AR modeling. And IID, so the samples are also IID. Samples of the noise are IID. It means that every sample is independent from the previous one or the next one, but they are taken from the same PDF. And then we replace it here. So we have this average, the sample variance of the noise, which should be minimized. We replace this eq'n with the value. And then just by expanding those parentheses and passing this derivation to inside and using the model, we easily come to this point, to this equation. And this equation is actually a Yule-Walker equation. In matrix form, if you just replace k with 1, 2, and so on, and up to p, we get these equations based on the autocorrelation function. And then we write it down in the matrix form. In the matrix form, we get this matrix of autocorrelation, times the vector of the quantities which we are looking for, and the cross correlation or autocorrelations based on different lags. So based on having no lag, or the first and the next sample, so the sample that we have with the next sample, with 2 samples beforehand, 3 samples beforehand, and so on. And this actually, coming to this point, is very useful because this autocorrelation matrix is actually having some properties. Those properties I have mentioned in another extra note that I already uploaded to the website, talking about the random processes and some features and properties. And then I'm talking about the autocorrelation metrics and the properties of autocorrelation metrics. I have enumerated more than 10 properties assigned to that, And one of the properties is that autocorrelation matrix is positive definite. The properties of positive definiteness of a matrix is that it's symmetric. So, and it's also Toeplitz matrix. So all the values, off diagonal values are the same. So R1, here you have R1, R2, you have R2. And it's Toeplitz, it means that if you have, for example, the diagonal term, you have R0 for all the elements. And for the upper triangular and the lower triangular, you have the same values for all. And this kind of matrices and the equations using this kind of matrices are easily solved using the Yule-Walker equation. Yule-Walker method is actually it's actually the Yule-Walker equation. And when you come up with the Yule-Walker equation, you're happy because there is a simple algorithm called Levinson-Durbin algorithm, which is very fast. And you can simply get these values A1 to AK or AP, whatever number of the coefficients, you can very fast, you can come up with that. So it means that even if you have the process, you have the LPC coding, you're not worried about that to be implemented in real time or not, because there's an algorithm called Levinson-Durbin, and it's very fast, so it could be real time implementable, and you can very fast get those AK values.
Which is the name of algorithm?
Levinson-Durbin algorithm. I will explain that algorithm also. It's called Levinson-Durbin algorithm. In MATLAB, even you just write it down, and you will get the algorithm in MATLAB already implemented. I will explain about the algorithm, but we don't have time now. We have actually run out of time. The derivations, you can easily go through that. I have written everything, so all the details are in these two documents. You can just go through that, and if there were any problems you faced with the derivations, just let me know that. Maybe in one of those review sessions I can, more detail, I can explain the algorithm. But in these 3 pages, I have mentioned all the necessary things that you need to know about the LPC derivations. Everything is here, and in the other document, you actually have everything related to correlation function and the whatever you need actually to know about the properties. So the autocorrelation, how it's derived, the autocorrelation matrix, the matrix form, and the properties assigned to that. So there are some properties related to the correlation matrix. So they are very nice properties, and they are taken from the linear algebra. So this matrix, which is called R in general, is a Hermitian matrix. So that's a very nice matrix, actually, Hermitian matrix. The conjugate is just symmetric. Then you have definitely, if the rank is, you have M, then you have M eigenvectors assigned to that. Is a Toeplitz matrix. So whenever Toeplitz property comes up, it means that you can easily solve it with Levinson-Durbin. Is positive definite. So it's also another nice property. And this all together means that this matrix even is possible to have iteratively get the new values for the matrix. So even if you want to get the matrix next sample matrix, you don't need to compute everything, because this matrix in every sample can be easily derived from the previous matrix in the previous sample. So iteratively you can get the answer, and here is what you have. So for m plus 1, you can easily use the one in the m and just add these values to the new matrix, and you will get it. So generalization of this kind of matrices is very easy. And you have an m number of the eigenvalues and eigenvectors assigned to that. And you will see later that what are the uses of eigenvalues and eigenvectors. These are all the properties, more than 10 properties I've mentioned. And then I talked about the power spectral density and the relation in the Fourier domain and its properties, and also the theory that we talked already the output of this LTI system. The output relates to the input in this power spectral density based on this equation, which is actually the magnitude square of the LTI system. So the output PSD is the input PSD times the magnitude square of the system, if a system is LTI. And we have the cross correlation in more detail, cross spectrum, and the coherence. And coherence is also a very important property, which for the extraction of the phase of the signal, normally we use the coherence. So it's actually the magnitude coherence is represented by the power spectral density normalized by the PSD of each of the signals. And somehow shows that the magnitude coherence is actually shows that in frequency domain how they are correlated to each other, two signals, how they are correlated. It's also showing if the system is LTI or not. So there's a kind of measure to show that if the system that you're passing the signal through, if it's LTI or not, you can also use this coherence. If the result is 1, then it's probably LTI system. So these are the extra documents that you can take actually, and in the afternoon we will talk about some estimation theory stuff. Very briefly, an introduction to the estimation theory and optimization algorithms. We don't go through the details, we just talk about how you can, if you encounter such kind of problem, how you can deal with it. So, you know, the random process by itself is a course. So that's just the lead of what I could give you. Just getting familiar with some definitions and some terminology. But if you want to know more, there are nice books about that. One of them is All of Statistics by Larry Wasserman from the Cambridge University. So you can, it's very simple and I think very general. You can get everything you need from that. Thank you so much, and if you have questions, I'm happy to get it. Again, don't forget for registration for the exam. Thank you.